In this video, we're going to look at two different examples of how to find singularities. Both of these are PR manipulators, but the first manipulator, you can see, moves in the YZ plane, and then the second manipulator can move in XYZ because the revolute joint is flipped. So let's first write down the procedure. Step 1 is find the forward kinematics. Step 2 is take the derivative, get velocity. Step 3 is find the Jacobian. Step 4 is set the determinant of J equal to 0 and solve. And there are two methods of how to do it. This one is the formula procedure. Or we can just do it by inspection. So looking at these by inspection, number 1 should have a singularity when theta equals 0 or 180 degrees. Because in that situation, it can't move in the y direction. That's its degree of freedom that got lost. It could move in the z direction, but it can't move in the y. Or it could even not move in the 0 direction because there are different positions that the prismatic joint could be in where it would sort of cancel out the height by the revolute joint. So here we're going to write our guesses. So now let's solve this out by math and prove if we're right. Step 1 is get the forward kinematics. This robot does not move in X, it only moves in Y and Z. So we'll skip X and just do Y and Z. So the Y is just going to be the cosine component of R. And then the Z is going to have the sine component of R plus the distance of the prismatic joint. So now we take the derivative, get velocity. So then we put into matrix form and get the Jacobian. Now here we remember the Jacobian is just going to be the coefficient of the joint velocities. So for the y, we have minus r sine theta. And then 0 for the d dot part. In the z, we have coefficient of d dot is just 1. And we have r cos theta. So then if we set the determinant of the Jacobian, so this is j, this is the x dot equals j theta dot. Then we set determinant of Jacobian equal to 0 and solve for what values of theta make that possible. So we'll have minus r sine theta times 1 minus this multiplication, which is r cosine theta times 0, which is 0. All that equals 0. So then we have minus r sine theta equals 0. Well, r is never going to be 0, so we get rid of that. So this is when sine theta equals 0, when theta equals 0 or pi. So this matches what we guessed up above. Now for the second manipulator, looking at this one, at any angle of theta, it can pretty much move in the XY plane. Theta only controls the XY plane. Z only controls the Z direction. So this robot can move in 3-dimensional space, but it only has 2 joints. Therefore, it cannot have a singularity. And we should be able to see this because when we get the Jacobian, it will end up not being square, and you cannot take the determinant of a not square Jacobian. So n is less than m. So there are no singularities. Fewer joints than degrees of freedom in the space. But we'll go through the process just to prove that there should not be a singularity. So looking at this, okay, if the robot starts out in this initial configuration, pointing in the negative x direction, then x equals negative r cos theta, y equals negative r sine theta, z equals d, where this is d. So then if we take the derivative of this, x dot equals minus r sine theta, theta dot, y dot equals r cos theta, theta dot, z dot equals d dot. So then if we put that into matrix form, we need that x dot equals j theta dot. So we'll have here x dot, y dot, z dot equals something times theta dot, d dot. So the coefficients here, minus r sine theta, 0, r cos theta, 0, 0, 1. You can't take the determinant of this. So this one has no singularities because the number of joints is less than the 3D space. This has more rows than columns.